Fran and I met about 5 years ago, well, it was 5 years ago this month, down in Florida. I did a lot of launch photography at the time, and I was at the launch of the Parker Solar Probe, and I had known Fran on the internet, on Facebook for a while, but we'd never met. And she happened to be at that launch as well, and so we started talking, and the rest is history. I mean, we had so many of the same interests, and she was traveling around the country at the time, and I invited her to come stay with me at my home, and we started working on some projects together over the years, and I guess she's been there, what now, 5 or 6 times, something like that, where we stay a couple of weeks at a time. And so we really have had a good time actually doing science. And Fran's one of the most interesting people I've ever known. So somebody who really is passionate about astronomy and really passionate about actually doing science with it.
Thank you. Okay, you'll keep track of that. Yeah, Hap and I, it's been amazing to get to know Hap. He has so many interests, and I can say he's been a great mentor, a great friend. He's got a really wonderful family that I got to know, and I was very glad and fortunate to actually get to know Hap and work with them in various projects, which we're going to just unveil quickly, and we won't keep you very long.
Okay, this is my observatory near a little town called Griffin, South Carolina. It's only an orbital 5 sky, so that's about as dark as it gets in that area. So it's fairly decent, and there's 5 of these on this property. So there was originally 10 of us astronomers who were sharing these buildings, each with 2 telescope peers in it. But this one, my partner decided to move away, so I bought his half of the building. And so this is where we do our work. Here's Fran with my plane weight rig, AP 1200 mount. And normally I do deep space astrophotography. This is a little collage of galaxies that I've done, and some of the nebulas that I've done. Yeah. So this is pretty much what I'm known for, at least amongst the amateurs. Here's another picture of Fran and I at the telescope. And this was there's an interesting story about this picture. This is in my warm room, and we've got TV and heater and kitchen and bathroom and everything there. But we go up there at night when she's there on the clear nights. And we had been there about 6, maybe 5 o'clock in the afternoon. We see it before the dark. And we actually, show you the actual data in a few minutes, but we were able to confirm, if you remember comet 2019 Y4 Atlas that was supposed to be the comet of the decade, we were the ones that confirmed it. The last data that went to the main atmosphere before they confirmed it and named it. Unfortunately, a few months later, it fell apart as it went around the sun. We'll show you some of that. Here's, Fran, you might want to say something about this.
It was the best thing to just be next to the telescope sitting there. It was
She said this was a 5,000 star hotel. So anyway, we like to shoot asteroids, and here's some animations. This one is called 492 Hyseni, and normally what I'm doing is just shooting 2 or 3 minute exposures with a 12-inch plane wave, and then putting them together into an animation. Go ahead. Okay. There's 6 TV. This is Eros right there. There's a comet and stars right there. And this one, we a lot of times we'll do negatives, inverse, so that we can see dimmer objects in the sky. This one almost occulted the star. This is the James Webb Telescope captured at the L2 point, 1 million miles away. So think about that. That's something the size of a tennis court. that's sitting out a million miles away, and it's plainly visible in the telescope.
And generally, these are some of the animations, pictures taken over a period of time. Could be a few minutes to like 30 minutes or so. And then you just put the pictures together, and you will see whatever is closest to us. It's going to move faster. And yeah, it's a really cool.
Yeah, so what we did, we started to actually start recording asteroid positions, because the Minor Planet Center is always looking for extra data. Some asteroids may have just been discovered, and we're trying to find their orbits. Other asteroids have been known for decades, and they will never turn down any extra data to continue to find their orbits. And the Minor Planet Center is based out of Cambridge, Massachusetts, and you can become a contributor. You have to get assigned an observatory number, minus 449, and you go through a process by submitting several different readings on asteroid position, asteroids. They want to make sure that you know how to use your equipment, that you're getting accurate times down to less than a second on the exposures, that you're getting very accurate right ascension and declination coordinates for each of the images that you put in. And once you do a few of those, then they figure you know what you're doing, and they'll give you an observatory number, and then they have a process where you just report data on the web, and it appears. We use a program called Astrometrica, which is really neat. It basically maps every pixel in an image to the right ascension and declination. And so when you calibrate it based on the STAR database, and when you see something in an image and you want to know what it is, you just click on that object, and it pulls it up out of the database to see what it is, what should be there at that position at that second. And it's extremely accurate. Let's see what's next here. Now, Pran was known when I first met her. I knew that she had an asteroid named after her. You want to talk about it a little bit?
Yeah, in 2017, some friends of mine decided that they were going to name an asteroid after my name, which was very surprising, and I felt very honored, and I feel very close to this asteroid somehow, emotionally. And it's the cutest one out there. It's about 13 kilometers in size, and it's between Mars and Jupiter.
When we first started working on it, there was very, very little data except the fact that it was an asteroid with a certain orbit, and that's about all we knew about it. And so I wanted to start doing some work on it and try to find out what its rotational period is, possibly the size and shape, and that sort of thing. This is the first time, this is right after I met Griffin. Came back home and shot this, and this shows it moving over a couple of minute exposure, and that was my first recovery of it. When I looked it up in Astrometrica, you can point to it, and sure enough, if you look right there, it looks it up in the database, and there's the name of it right there. So we knew we had it. Now here is a video of it moving. Now, incidentally, if you look over to the right, there's another asteroid on a parallel path.
That's my twin.
But her asteroid is right there in the middle. So we've been visiting it every time we can. It's on this side of the sun. Sometimes it's on the other side of the sun, or it's out. It's in the daytime sky. We can't see it, but every time that we can, we take a visit. Now, one of the tools that I wanted to work with is to do light curve analysis on it, so we can figure out what the rotational rate is. And basically, it's very simple. As asteroids rotate, most of them are shaped not symmetrically. They're shaped like a potato or something like that. And so as they rotate, the reflected light, sunlight from them, as we pick up in our scope, varies. And a lot of times it will vary, in magnitude or maybe less. And so by plotting the light curve, you can figure out how fast it's rotating. Here's bending. Now, this is a very symmetrical asteroid, so if it rotates, it's not going to have much of a light variation. But this one This one will. This is a very oblong sort of thing. And you can kind of look at the total amount of light power coming from it over time. You can see how this would have quite a varied light curve. And this one has a complex axis in relation to us, and so its light curve is going to be very complex. Okay. This is a typical light curve. You can see the magnitude over on the left. It will vary by about 0.3 max or something like that. And you can see the phase angle down at the bottom. And you can also measure, grab a light curve at various points on its orbit around the sun and how our viewpoint changes. And by mathematically analyzing all of that, although I haven't got that far yet, you can actually figure out what the shape is of an asteroid, because its light curves can be different from different viewpoints. Now what I use is a program called NPO to measure light curves, because obviously if you're just looking at one star, then light variations due to transparency of the atmosphere, to seeing conditions, to clouds passing over, is going to affect that one star. But if you look at a number of other stars that are in the field of view that are known to be constants, not variable stars or anything like that, then they will all change in brightness at the same time. And so you can kind of take the variation out of it, and you know that this curve you've got is pretty accurate. And this was my first attempt at a light curve brand that doesn't repeat, so I didn't have time enough to get the whole thing. So it's not a complete cycle yet. You can see the fractions of a sidereal day at the bottom, but we want to keep on working on this.
That was very great data by Hap, because since he was unable to get a full light curve over one night, this immediately told us that this asteroid probably has a much longer period of rotation if you cannot just wrap it within the nighttime. It has to go to second night or 3 nights. And since I'm a student at UC Santa Cruz, so I'm very fortunate to live very close to the observatory in San Jose, about an hour away, which is actually operated by the Department of Astronomy of our university. And they have really amazing telescopes there. So some of the professors at my university were doing a lot of observations of galaxies and quasars and all of that distant stuff, where as I deal with planetary in the solar system, mostly asteroids and comets. And then I asked
Go ahead and turn it towards you. There we go.
So I asked one of these professors, I said, is it possible that within that time frame when you have time in the telescope, you're taking the spectra of these stars and galaxies, can we perhaps take a spectra of the asteroid that is named after my name? Because I was very interested to understand the composition of it. Because it's so small, it's only 13 kilometers. Nobody's going to care to study 13-kilometer asteroid that nobody has heard about. So I was simply out of curiosity to know what's the spectra of it, what's the composition, and some more details. And they said, sure, we can totally fit you in our schedule, and we went and scheduled that. But they also were asking me, they said, do you know how fast this asteroid is rotating? Because it's very important to know that when we take a spectra, are we taking the entire surface or only one-sided? Because the spectra generally tends to change from one side to the other. It depends in the asteroid. So we weren't sure about that because Hap wasn't able to finish all of this. So I reached out to some friends, and so this is just another picture of the telescope. It's a 3-meter telescope at the observatory. That's what we take the spectra with. And so when I reached to some friends of mine, a group of astronomers in California, and I asked them that I needed a light curve of the asteroids because I do not own the equipment. I don't have large advanced telescopes like Hap does. So these astronomers, they actually were able to measure the light curve over a period of 5 days. You can see the dates here. And they determined that the period of rotation for this asteroid is actually 18 hours, which was very surprising given the small size that it has. I was assuming it would be 2 or 3 hours, but then 18 hours was quite long. So it was a great information to have prior to measuring the spectra. So then the astronomers at the observatory, they started to take a spectra of this asteroid. So this is the slit of the spectra, and that's a star, and next to it, that's where the asteroid is. And it's funny because Professor Raja in the astronomy department, he said, I've done spectra for 40 years. I've never taken a single spectra of an asteroid before, because he always deals with galaxies and everything. And it was very interesting and exciting for him as well to try something new.
We were watching over remote control because she's in California and I was in South Carolina. And we were basically,
We were looking over the shoulders of the astronomer site. And in order to take a spectrum, they use a slit spectrograph, where they have to keep the object, in this case for asteroid, in the slit. But they don't want to allow any other stars to appear in that slit because the extra data there would spoil the spectrum. So it was interesting. This was in a very dense part of the Milky Way at the time, so there were stars everywhere. And as he was tracking the asteroid, he had to actually manually steer the slit as it went through the star field to make sure that no other stars fell in the slit. And I just thought that was really nice, really neat.
And this is the spectra of it. This is how it looked like. This is the raw spectra, and then this is two spectra from two different nights. And this is after it had already been subtracted from the sun's spectra. So this data is still under process because this still needs a lot of correction so that we can actually find a Gaussian fit or some model so that we can make this very raw spectra to look a little bit nicer so that we can actually identify all the peaks. But this is really nice. This is something I'm working on the side. This is not of my school study or anything. This is just pure curiosity with Hap and I that we do as amateur science, and luckily we have access to some of the sources like this that we can actually be able to do. The other thing that I'm very interested in, and actually is one of the things that got me interested in asteroids and comets and minor planets in general, is the occultation of asteroids and how we can learn the shape of them without even having to go over there and look them from the close. So you can think of the occultations similar to a lunar or a total solar eclipse. For instance, you have a star here, and for instance, you can think that this is the sun, and then you have the asteroid, like it would be the moon, and then you're projecting a shade somewhere in the earth. And since these asteroids are very small, the shade that they're projecting, generally it's not this big. It's a lot smaller. Sometimes it's just like a kilometer long or so. And in this field, there are going to be different observers that are going to look for this particular asteroid to occult the star, and each of this is going to report the shade happening at their location at a certain time. So they have a device that is very precisely located with the GPS that will record your time very precisely, and each of these observers then will report if they saw the occultation or not, and then will report their timing, and once they do that, they will be able to actually generate the shape of the asteroid. So these are all the observations, all the people with their telescopes, and this is the path of this double system asteroid. This was Asteroid. And this is like a twin system, and these are all the observers that were able to report there. So these guys, for instance, missed it. They couldn't see it. But even if they didn't see it, that's still good because it tells us that this asteroid's shape doesn't continue here. It kind of stops here, and that's how it is. And it's just incredibly amazing, this method, how they do it. And then this is after they made all the models, and they were able to fit and learn how the shape looks like. And I was interested how to learn the shape of my asteroid other than the light curve, which was also pretty tough. So I had to go in a software because there's particular software where you can search for an asteroid and you can see if it will occult a star at any point in time. So I looked at my asteroid, and interesting enough, I saw this path that went right over the United States. different astronomers in the area. I'm in touch with all of them, and we all heard about this, and we all got set up our telescopes in different areas of San Jose and Santa Cruz, and we all got ready to wait to take all the observations, and it cut it out. So none of us was able to actually record any observations. And a few months later, there was another observation going through mid-Europe and passing right over London in the UK, and it was winter, so it's UK, it's always cloudy, so I wasn't even, hoping for anything. So I still haven't been able to get any data, but hopefully sometime in the future.
Okay, here is an interesting story. Fran was at the observatory one night, and we had been observing and filming and shooting asteroids all night long. And it was a full moon that night, and this was about 5 a.m. in the morning. This is in January, so it still isn't light. The full moon was still hanging over the west, and we were about to just conk out totally. And Brand said, let's try one thing we've never done before, and the Minor Planet Center keeps a record of objects that have been just recently discovered that need confirmation. So we looked, and sure enough, there was a comet. At that time, it had a weird name, which was CK19040 or whatever that is. And we were able to, it was a magnitude 19.3, which is dang dim, especially for the full moon. And I thought, well, we'll never do this. And it was over to the east, maybe only about 20 or 30 degrees up. So we thought, let's try it. So we went over there and we shot a couple of 5-minute exposures. And sure enough, Fran was able to see a slight tail on it. And first we were able to detect it and tell that it was not just a rock. And so the next morning, I gave this data. This is our coordinate data here. This 449, the last 3 digits here is your observatory number. So I submitted this to the Minor Planet Center. And you can see down here, here's the observatory 449, the Griffin Hunter Observatory, Bethune Observatory, Pranvera and Hyseni, measurements myself. And the next morning, looking at the bulletins, is this. Our data was the last data needed to confirm it and name it. And so this was given the name of C2019Y4 Atlas. So this was Comet Atlas that occurred early in 2020. And we thought, well, this is cool, But about a month later, I started reading in some of the magazines and the flyers, this comet is brightening tremendously and could by March or April become the comet of the decade. I called Brand and I said, guess what we helped confirm. And so I started shooting it every night I could. Unfortunately, this asteroid or this comet had been around the sun several times and weakened. And apparently, when it passed near to the sun in late March or early April, I don't remember which, it fell apart. And so it never became visible to make it out. But we were proud to at least have a piece of the action there, so to speak. This is a picture of it. I shot some, tracking on the comet, and you can see the stars are streaked there. But that's C2019Y4 Atlas.
So Hap and I also have been looking at different citizen science programs we can participate, whether we can see with our telescopes or with this telescope, we can perhaps get data from larger telescopes. And there is this program called ISAC, which will allow you to be part of it. Any of you can be part of it. And you can apply and you can get in these different campaigns they offer every other month about asteroids. So they use data that they take from Pan Stars Observatory in Hawaii. It's about almost a 2-meter telescope. And this telescope scans the sky every single night, trying to look for new objects, new asteroids, because there are so many and they can discover every single night. But of course, all this data, it's a lot, and they need people to participate, to look over the data, but also this is a great cause because it could inspire and get the public involved in searching for new objects. And Hap and I have been lucky to be part of this program for a number of times now. This is the camera.
The camera is very special. It's a huge camera. The whole system is designed to very low F ratio, a large sensor camera designed to take pictures of wide swaths of the sky. And you can see this is actually constructed from a number of other camera chips. But over the years, a lot of them failed. And so this is basically the good pixel map of that camera right now. There is a new telescope called ES2 that has a much newer camera that we work off of now. Slides on that.
And this is how we usually receive the data. It's generally 4 pictures taken, I believe, 5 minutes apart from the telescope. They send the data, we download it in our computer, and then we put it in the software in Astrometrica. And then these are inverted, so you know the stars are looking dark, which is the inverted. And we do this because it helps us visually to identify these. And then we start blinking these images. The software allows you to blink them apart. We zoom in, and then we stare at the monitor for a few minutes to see what's moving in there. But also, you have to be careful because sometimes there are things moving that could be a bad pixel, and you could mistake it for an object. But I guess this is also, when you do this a lot, you kind of get used to it, and you can recognize what's a bad pixel and what's an actual object. And sometimes you also see known asteroids, like if you see something moving, you just put it against the database, and the database will be able to recognize that this has been discovered, let's say in 20 or 2000 or something like that. And sometimes that's disappointing, but you know, it's fun. But sometimes we also see a lot of objects that the system doesn't recognize, the database doesn't have any information. So in that case, we have to build a report and to submit it to the observatory so that they can submit it to the Minor Planet Center. This is a general report, how it looks like. So you have all the information here. This is the code of the observatory of the pan-stars. We are the measures. We're considered measures, I guess. The observers are the ones who collect the data. And we have the 4 pictures. And if you see, sometimes these asteroids happen to be in the corner of the image. So you will see the asteroids in 2 frames, but not in the other 2. So unless you don't see the asteroid in 3 frames, they are not going to accept the report. So you want to make sure you have at least 3 measurements, or 4 in this case, to observe it. This is just one of them. We just gave it a temporally designation. This was number 27 that we had submitted at that time. It was magnitude of 21. But since then, we have submitted close to 100 asteroids. And all of these are going to the Minor Planet Center so that they can check on these reports and see if these actually are real asteroids, the new ones, or they had been discovered in the past but been lost. And this is data that helps them refine the orbit and find new asteroids.
Right, this one, they have some criteria. They have to be a certain signal-to-noise ratio and all this sort of thing. This one was about magnitude 21 point something when we reported this one. This is...
Usually we're not always in person together, so we sometimes do the work together when I visit them, or we just jump over Zoom and then we work together. Sometimes I do the blinking, he builds the report, or like he does the blinking and I do the report, or sometimes we do the blinking both, because sometimes I miss things, sometimes he misses things, just to kind of be sure. And this is my goofy face every time we look for asteroids. It's always exciting, my favorite thing to do. This is an animation which you would probably have to play.
Well, this is an animation that we haven't been able to make work, because again, we put it together on one laptop and displayed it on another laptop, so it doesn't have proper coding for it. But this is a typical frame, or piece of a frame. It's zoomed in. And if you look at, I'll tell you what this was, if we could move. This little dot right here
Go ahead and go back a slide and then go forward a slide and then you can play it again.
Really? That's right. There we go. Okay, great. So you can see it move. And that's the 4 frames. And they're taken about 5 minutes or so apart each. So that's a typical submission. We would see that, we check it against the database, it's not there, so we have to plug it in.
And interesting enough, 6 months later, after we submitted this very particular one, we heard that this was actually a brand new discovery, and this was very great news. In fact, I don't know if the audio is somewhere in here, where I called Hap to tell him that we discovered an asteroid. So I would like to share that with you from July of 2021. And if we could maybe play that.
Hap, I just forwarded you the email, so check it out. I quickly checked out the list. I saw our name in there, but I wanted to look closely and be sure that we actually discovered one. I'm super excited, and I'm like right in the start party with a lot of people, and I just can't look at it right now. Please go check your email like right now. I know there's something but I just don't know what it was about, so read it carefully and tell me, okay?
Well, it says we have one provisional that has the name of 2020 SS13, so I'm going to try to find it on the MPC and see if it's in the sky right now.
Discovered? Like a preliminary discovery? Like you and I, for real?
It looks like it. It's 2020 SS13 is what they have it listed as, and I just looked it up on the MPC, and it's magnitude 25 right now, so it's probably not visible from my scope anyway, but I will give it a shot though. As soon as I can get back up, I haven't looked to see what part of the sky it's in. But as soon as I get a clear night, if it's in the sky at all, I will try to shoot it using some long exposures and see what I can get.
All right. So these are the certificates that we got.
And this is the official designation, 2020 SS13, although when we heard the news that we discovered this was in July of 2021, it of course takes several months for them to confirm that this had been discovered months ago. And if you go to NASA's JPL database, and if you type SS the 2013, you will be able to find some of the information, although there is not a lot of information because the only observations of this asteroid has been from Hap and I. So we still need more observations to be able to confirm and get more data on this so we can know how large it is or other information. And if you go to the Minor Planet Center and look at the ephemeris, this is how it looks like. So you can find out the coordinates, you can see how bright it is. This is the magnitude. So right now this is very dim, which is impossible to capture this from Hap's observatory. And we're trying to maybe cooperate with larger observatories so we can actually get another observation. And then once we do that, we will be able to name it. And since I've got one named after me, it's probably going to be named after Hap. So,
Okay,
This is the position, you can look this up at the small body database at JPL. And this was it on the date that we discovered. And you can see where the Earth is right there, and the asteroid is on the same side of the sun as the Earth. So that's about as close as it gets. And it was at magnitude 20-something. But now, go to the next slide. This is the position right now. You can see where the Earth is, right? That's what's the blue. Yeah, there's the Earth now, and there's the asteroid now. They're on the same side of the sun. But it'll be another year, a little over a year, before the Earth will come all the way around again. The asteroid is a little slower, will be opposite of us again. So this is the best chance that we've got to recapture
in about September, October 24. So that's the plan. We would like to be able to be the ones to actually confirm it. And we can talk about trying to get the bid to do it.
Yeah, I will try to, since we have, I have access to university's observatory, maybe we will get to convince the university to go, after it, so I don't know. Thank you very much, everyone. If you have any questions, I know it's been a long day, lots of talks, but thank you very much. I'm so happy to be here, and so it's I do have a question.
Yes, so when in next year, what are the chances of you guys finding it? How accurate is your prediction?
Well, when it was first discovered, they were listing it as 20.5, something like that. And I know that I can see that part of the comment that we've been.
But I mean, my question has more to do with the orbit. Like, will you be sure that the one you see next year, how sure will you be that that's the one?
Right, that's part of the whole process, is that we observed it 4 times over about 20, 25 minutes. And so from only those 4 positions were they able to extend that out into the future. And so we can predict where it's going to be this time next year. But again, there's only 4 observations to support that. So it probably is a little bit one way or the other. And I'm going to use my 12-inch planeway because the field of view is big enough where if it's a little bit off of its orbit, I can still see it in the frame. I may have to hunt for it a little bit. And I know I can get down to -20 or magnitude 20. So I'm hoping I can pick it up about this time next year. And again, if not, she's going to try to get her friends to do it.
Will you be able to try to hunt for it in those frames again, or?
No, that comes from the ISC, and they give out, they send you frames basically off of their
Yeah,
schedule.
it's like we can decide the data
Right.
they send
We don't
us.
know where they're aiming the telescope.
Is there a chance somebody else will confirm?
That's what I'm hoping.
Okay.
That's the point. They give you a preliminary nomenclature, which is what 2020 SS13 is, and they wait until somebody else finds an asteroid at that point in its orbit, and if everything matches up, then they confirm that's yours, and at that point they get back in contact with you and you can name it.
Thank you very much, everyone.